Hello everyone. Welcome to my presentation of our work, Input Normalized Stochastic Gradient Descent Training for Deep Neural Networks. So here is the outline. I will start with the introduction and then discuss the related works. Then I will go into the details of the algorithm and the methodology. Then I will present the experimental results and I will conclude the presentation. So the idea of input normalized stochastic gradient descents comes from the stochastic gradient descent itself and its limitations. I want to start with a brief overview of the stochastic gradient descent, short for SGD. Assume an input-output pair of x and y and a set of weights w. A neural network model predicts the output using a nonlinear function f, and we define the cost objective function of the model as L. So here the nonlinear function f uses x and w to return the output. The aim is to find the optimal set of weights that returns the minimum cost. And SGD is developed to avoid extensive computation, and it presents an iterative method to estimate the weights. You can here see the formula. It utilizes the gradient of the cost function with respect to the current set of weights and a single training example. That's where the stochastic comes from. So SGD is itself simple, easy to implement, but it has limitations. So the second inspiration to the INSGD is the normalized least mean squares, abbreviated as NLMS, commonly used in adaptive filtering. So I will also briefly go over it. Assume an input U and a set of weights W. The desired output of the system is D, and the linear estimation problem is defined as here for the jth iteration step. So a conventional LMS algorithm updates the weight iteratively, similar to the SGD, using the input and the error, which is the difference between the desired and the predicted output. So you can see the LMS algorithm here. Although LMS algorithm leads to convergence under convenient circumstances, it also has limitations originated from the input signal. Therefore, normalized least mean square algorithm is introduced, and it incorporates the power of the input signal to improve the convergence and stability. You can see that the update term now has a normalization factor. NLMS normalizes the update term with the square of the L2 norm of the input signal. Inspired by the NLMS and SGD, we combined the strength of both and created the INSGD algorithm for training machine learning models, and I will go into the details of the algorithm later. Before that, I want to briefly show some normalization based optimization algorithms commonly used in machine learning operations. So first is the ADAGRAD. It is developed to make the learning more adaptive, and it divides the gradient by the accumulated square of the gradient itself. RMS prop does the same thing with a slight difference. It uses the weighted average of the gradient to divide the update term, and ADAM uses first and the second order of the gradient to update the weights. Layer-wise adaptive rate scaling, abbreviated as LARS, uses the power of the layer weights for the update, making it layer adaptive. So layer-specific adaptive learning rate also utilizes the logarithm function to escape the saddle point. So the logarithm function is actually critical for our algorithm, which I will go into the details now. So now I want to show the details of the INSGD. Assume there are only linear neurons in the last layer of a network, and the desired value of the ith neuron is di. Therefore, ideally, we want di to be equal to the dot product of the optimal set of weights and the input. However, the initial weights does not provide that. The problem is the optimization of the weights, and we want to find a set of weights that returns the minimum of the squared error of the weights, such that the dot product of the weight and the input at the kth iteration equals to the di. Using the Lagrangian multiplier method, we can find an adaptive iterative algorithm which is itself equal to the normalized least mean square equation. So here we use the square of the L2 norm of the input to normalizes the update term. Now assume the neurons are nonlinear, so there is an activation function. However, this does not change the problem and the solution obtained by the Lagrange multiplier if the function has an inverse. So it is not a big problem for us. And here I want to add that almost all the activation functions used commonly in neural network models have inverse. The update equations becomes like this. So only difference here is the use of the inverse function in the definition of the error. So using this assumption on nonlinearity, weights of every layer in a deep network can also be trained. So we can replace the dot product of the error and the input with the gradient of the cost function with respect to the weight, and we can normalize it with the square of the L2 norm of the input. And for further details, I would like to show our algorithm in a diagram so you can see it better. Here, for every layer, the input to be normalized is different, and we used the input to each layer to calculate the normalization term in our algorithm. And I will stay 5 more seconds here just for you to see it more. Now, before I go into the experiments, I also would like to show some improvements we had in our on our algorithm. So we decided to further improve the algorithm by using the momentum as in the SGD and calculate the input momentum term to avoid the outliers in input data. Here, P is the weighted average of the square of the L2 norm of the input, but I also want to add that the L2 norm is not really necessary. One can also utilize and use L1 norm as we did in our experiments. So having an L2 norm or L1 norm is a choice, and one can select any to train their model. We also took some inspiration from one of the related works and used the logarithm to balance the input power to avoid it being too large or too minimum. So we decided to use logarithm. And to avoid the division by 0 or a negative value, we also use the regularized function, which you can see the details here. So now I want to present the experiments. We trained the CNN models and a vision transformer on computer vision, specifically image classification tasks. So we use CIFAR 10, CIFAR 100, and ImageNet 1K as the benchmark datasets, and use ResNet 20, White ResNet 18, ResNet 50, MobileNet V3, Vision Transformer, and a toy network for training. We then compare the results of the INSGD with the other optimizers. So the first experiment is on CIFAR 10 and carried out by training ResNet 20. All the results that I am going to show here and in the next slides are repeated with the different seeds, and we present the mean and the standard deviation of the accuracy results on testing datasets. So you can see that in optimal training settings, INSGD, both L1 and L2 norm outperforms other algorithms. We also this was the first table, and in the second table you can see that we have tried the larger batch size since INSGD is input dependent, but still it showed better performance. The INSGD showed better performance than the SGD. Here we present the convergence graph of the ResNet 20 training. You can see that INSGD, both L1 and L2 norm, converges better than the other algorithms. So we decided to train the MobileNet v3 since it utilizes the depth by separable layer in some blocks rather than the convolutional layers. So you can see that in optimal training settings, INSGD L2 norm performs superior to the other algorithms. So in order to show the performance of the INSGD, we also used a toy network with 4 convolutional layers. The objective is to understand if the performance improvement is caused by the INSGD or the models are too perfect to be trained with almost anything. So therefore we decided to use a toy network. But it is obvious that the INSGD can still outperform the SGD in image classification tasks, specifically on CIFAR10. Here you can see we trained the toy network with the different initial learning rates, and in each INSGD performs better. So one suggestions from the reviews to us was to evaluate the performance of the INSGD with a model having no batch normalization layer, since INSGD normalizes the input in the backward propagation. Here you can see that although an advanced model like ResNet can recover from not having a batch normalization layer when it is trained with the SGD, a toy network diverges. But this is not the case when it is trained with the INSGD. The performance only drops slightly. So far we tested the performance of the INSGD on the CNN, but it is ideal to test it on Transformer too. Therefore we also tried Vision Transformer. Here, although INSGD has a better performance than the SGD, Adam has the best accuracy results overall. Now I will present the experiment details on CIFAR 100 and ImageNet 1K. For CIFAR 100, we used wide ResNet 18, and for both top 1 and top 5 accuracy results, INSGD performs better than the SGD. Similar to CIFAR 10, I want to present the convergence graph of the wide ResNet 18 training on CIFAR 100. And in optimal training settings, INSGD converges better. If we further zoom in the graph, you will see that. Finally, the results of the training ResNet 50 on ImageNet 1K. So we had an improvement of 0.32% mean accuracy with the help of INSGD compared to SGD in ImageNet 1K training. To conclude, we presented the INSGD and we believe that it can offer solutions to eliminate the limits of the traditional optimizers by leveraging input normalization. Here we only tested input normalized stochastic gradient descent on image classification task, but it can be extended to various tasks. We also note that INSGD algorithm can be further fine-tuned for training of Vision Transformer and MobileNet v3 since they uses different blocks than ResNet models. And thank you so much for listening. My name is Salih Furkan and I present our work, Input Normalized Stochastic Gradient Descent, in the name of our group in the university under the supervision of Professor Enis Cetin in University of Illinois Chicago in ECE department.